Okay, well, uh, let's continue where we left off last time. Uh, it'll take a while to get the whiteboard on. Hopefully not too long. Uh, well, it's a new board. And I don't know where my way around this one. Thank you. Station. Okay, make a full screen. Okay. Uh, uh, Come on. I will try a different board. This one is okay. Second attempt. Um, uh, uh, let's uh, uh, let's briefly recall where we stopped last time. Last time we started proving the Jordan theorem. And there were two assertions in this theorem. the first assertion says that if we take the n sphere, subtract subtract an n ball, the result will have zero homology groups, zero reduced homology groups. And if we we take what homology groups we take basically any homology theory which has a continuity property, and then well, as an example, we could take the classical homology theory with z coefficients. We haven't seen any other coefficients yet, but we will do so today. And well, and I is a continuous injective map. And well, we actually proved the first part. Let me see if I can get spotlight. No, eraser, no, color. Yes. Okay, so we did prove this part. And the second assertion, which actually is Jordan's theorem, as follows. The homology of Sn minus I of Sm is the same as the homology of Sn minus I of Sn minus 1. But I need a shift. It's not these homology groups are not isomorphic as they are. We need to shift one of them. Timur, how exactly do we need to shift these groups?
The second one should be star plus 1.
Okay, well, let's see. Let's see an example. If I take S3 subtract S2, I have the reduced homology in degree 0, and if I take S3 and subtract S1, I have reduced homology in degree 1. So I think it should be -1. For example, n equal 3, m equal 2. Then and h equal capital H. Then on the left we have z in degree 0, and on the right we have z in degree 1. And well, the second part follows formally from the first one. Basically, all we need to do is I'm sorry, I'm having troubles with I'm having difficulties with the control panel. Wouldn't let me write on the board. Anyway, so the second part follows formally from the first part by just using the Maya-Vitoris sequence. And well, I forgot to mention that here I is again continuous and injective. Okay. Now the second part follows from the first part, just by formally applying the Maya-Vitoris sequence to the sphere Sm, represented as the union of two disks and such that the intersection is Sm minus 1. I think, so as a consequence, we have Sn minus the union is intersection of so Sm minus the union of two disks is the intersection of the complements of the individual disks. And I think the details can be left as an exercise. Timur, do you agree?
Yes.
Значит, дополнение к объединению — это пересечение дополнений.
Мгм.
Для каждого индивидуального дополнения по пункту 1 мы знаем ответ.
Мгм.
Значит, ответ равен нулю.
Мгм.
Значит, значит, теперь значит, пересечение дополнения — это то, что нам нужно посчитать на значит, следующем шаге индукции.
Мгм.
Значит, значит, соответственно, да, значит, это у нас, значит, это у нас будет меньше, значит, меньшее множество в Майре, то есть, а большее мы, значит, мы знаем по предположению индукции.
Мгм.
Значит, Тимур, я думаю, что ну, то есть, будет очень хорошим упражнением, значит, взять, расписать Майра Виториса и вот посмотреть, что получится. Okay, I'll write again the components of the Maya-Vitors. So we have U equal Sn minus I of dm plus V equal Sn minus I of dm minus. And then we need to understand what is the union union V, what is the intersection, the U intersected V, and then once we understand that, we just plug the result into the Maya-Vittor sequence, and we observe that the no, sorry. Okay, true. We just observe that what we end up with is exactly this isomorphism. Тимур, хорошее упражнение и несложное. Значит, очень рекомендую проделать.
Хорошо, кажется, я понял.
Okay, well, let's see. Okay. So we have the Maya-Vittor sequence, and we get the result we're after, and in particular, corollary. S2 minus a closed simple curve has two path components. In fact, Jordan proves more. Both of those are homomorphic to an open disk in the plane. But this is not for free, and there are several proofs. There are topological proofs, and also there are proofs which use complex analysis in one variable. But anyway, the statement that the complements of disks is requires some extra work. And in dimension 3, there's a similar statement, but it is no longer true that both components are disks. And there is well, as an example, there's Alexander's horn sphere, which can be found in Hatcher's book, and it's a wild embedding of the two sphere into in three sphere, and one of the components of the complement is not simply connected.
Can I ask the question?
Sure.
Like, am I right that if we want to know something about path components, we should watch at 0 degree homology?
Yes. Actually, the homology in degree 0. Well, that's let me write it. Like this. The standard homology in degree 0 is the free abelian group generated by the path components.
Yeah, and to show this corollary, we should apply like the theorem to S2 minus the embedding of S1. But if we get it like on the left-hand side as a 0 degree homology, then on the right-hand side we will have -1. homology. And
well, we start with S. We start with S naught, and for S naught, the complement is just a circle. Then we use the second part of the theorem to pass from S naught to S1. And well, the circle has reduced homology in degree 1, and the complement. Sorry, no, the complement of S naught in S2 is a circle, and it has reduced homology in degree 1. Okay, now we pass to S1. From S naught to S1, and we get reduced homology in degree 0, which is the same as in the previous case in degree 1. So the reduced homology in degree 0 is Z, and so the non-reduced homology in degree 0 is Z plus Z, which means we have two path components. Does this make sense?
Yeah, I see now.
Okay. Well, let's see one more application of Jordan's theorem. The next theorem is called the theorem on the invariance of domain. Now, what does it mean? Well, it means suppose I have a continuous injective map. Of topological N manifolds. Well, let me call this map F. Then F is open. What does this mean? Well, this means it takes open sets to open sets. Okay, step one, it suffices to consider the case when U is an open ball. Sorry, M. M. The source manifold is an open ball. Well, let's assume this. And moreover, the target manifold can also be assumed to be an open ball. Now let's think. The let's think. Well, the open ball is homomorphic to Rn, so I will just write Rn everywhere. So in other words, I have a map from Rn to Rn, which is continuous and injective, and I need to show that this map is open. Well, let's take an X. In Rn and a small disk. Well, actually, we don't need a small disk. We could just take any disk. Oops, what happened? Brilliant. Okay, I think I've just erased something. I didn't mean to. Anyway, so I have a disk. Which contains X in its interior, and I want to show that that the F of the interior is open. Now let's consider F as a map from Rn to Sn. Where Sn is the one-point compactification of the space Rn. Now F of sorry, I will okay. Okay. Sn minus F of ds, sorry, delta d has two path components, and here we use Jordan's theorem. Well, those path components are as follows. One is F of D circle, meaning F of the interior of D, and the other one if it is Sn minus F of D. And both of those are open. Why? Well, Sn minus F of something is this thing is an open subset of Sn. And so the path components are the same as so the path components are open. Why? Because Sn is a manifold, and as such, it is locally path connected, which implies that all path components are open.
Why is this true?
Why is this true? Well, let's let's recall the definition of a locally path connected space. Well, let's say a space X is locally path connected if for all X inside X, and for every open U that contains X, there is an open path connected V such that X is in V and V is inside U. So, in other words, every open neighborhood contains a path connected neighborhood. Well, exercise. The path components of a locally path connected space are open. Okay, let me erase this. Exercise. Path components of a locally path connected space are open. Well, which basically follows straight from the definition. Okay, Timur, do you have any questions or objections?
No, that's clear now.
Okay. Well, suppose we have M and N topological manifolds. Without boundary. Now, when is it possible to have continuous injective, surjective, or bijective maps from M to N? So, if
maybe if M is less than N, we have an injection.
Yes, well, obviously, if we could have injective maps from a lower dimensional manifold to a higher dimensional manifold, we could have surjective maps going in the opposite direction. But let's see if there are any none of these restrictions. So first of all, if M is less than N, there can be surjective maps from M to N, and these are space filling curves, basically. We'll try to let me try to do something with okay, space filling curves. But there are no continuous bijective maps. And this follows from the theorem we've just proved, and it's one of the exercises in the first problem sheet. So this is what happens if m is less than n. So in other words, there is a non-obvious part which says that there are there are surjective maps, or at least for some m and n, there are surjective maps from n to n. Despite the fact that the dimension of m is less than the dimension of n. And well, one such example is space filling curves. Значит, понятно ли, о чем речь, Тимур?
Да, я только Тагир.
Тагир, да, я прошу прощения.
Ну да, там понятно.
Okay. And well, if m is greater than n, there are no injective maps injective maps from m to n onto why not? Well, let's see. Well, if we have an injective map, injective continuous maps. Well, let me just put continuous here. Well, if we have an injective continuous map from a high dimensional manifold to a lower dimensional manifold, then what? Where can we find a contradiction to give?
Maybe if there are an injective map, we have some injective homomorphism on higher homology group of M.
Too complicated.
No.
The image would be if such a map existed, the image would be opened by the invariance of the domain theorem.
Mm.
So such a map so we may assume that m is so we may assume that the map is also surjective. so we may assume that the map is surjective. And then it would be open by invariance of domain. So it would be a homeomorphism, and we showed a few weeks ago that we can't have a homeomorphism between manifolds of different dimensions.
I don't understand why we can assume that it's surjective.
Well, we just replace the images open, so it's again a manifold, and we replace n with the image.
The image of M is open.
Yes, it's an open subset of manifold, which makes it also a manifold.
Mm-hmm.
Does the rest make sense?
Yeah, the rest is clear.
Okay, so there are no non-obvious maps or counterintuitive maps from a higher dimensional manifold to a lower dimensional manifold. Тимур, чем вы занимаетесь? Кто вы, научный руководитель?
Андрей Дмитриевич Рябичев.
Да. В общем, в алгебраической геометрии есть, значит, похожее утверждение, теорема кого? Теорема, значит, Зарейского, насчет том, что значит, если у нас есть отображение, значит, многообразия, которое объективно на комплексных точках, да, многообразие на C, которое, значит, объективно на замкнутых точках.
Mm-hmm.
Если кто откуда бьет это отображение будет нормальным, то, значит, то отображение будет на самом деле изоморфизм многообразия. В общем, такие утверждения, значит, есть не только в топологии, там, в разных других областях, и ну, они осмысленны, и они, в общем, полезны, требуют каких-то доказательств. So this, the statement, the invariance of the main theorem, which we have just seen as a topological analog of several other statements, and in particular there are similar statements in algebraic geometry, which, for example, if we have a map of complex algebraic varieties, which is a bijection on closed points, and the source variety is normal, then the map is an isomorphism. Okay. Um, let's see. So uh, we also need to talk about what about homology with coefficients and well, let's have a break first, and then we'll talk about homology with coefficients, which is a different topic. So let's first have some refreshments and so on, and then we'll continue.
Oh, okay. And how many times?
Well, let's say 20 minutes.
Okay.
Okay, so let me try to write this here. Group. Okay. Okay. By the way, we've just we've just talked a little about topological manifolds and when exactly we may have non-obvious maps from manifolds of higher dimension between manifolds of different dimensions. And well, the answer is there are space filling curves and they're analog and they're analogs, but apart from this, there is nothing else. All other non-intuitive options are excluded by the invariance of the main principle and again its consequences and this principle is an analog of Zariska's main theorem in algebraic geometry, which has many versions, and well, one of the versions says that if we have a morphism of varieties over C, which is a bijection on complex points, and under some assumptions, which I probably got wrong in the first half, namely well, the source is what it is, but the target must be normal, which is a version of smooth in the topological case, but weaker. Then this morphism is an isomorphism. Well, let's see. So now we need to talk about homology with coefficients and also cohomology. But suppose we have an abelian group and a space, then we define the homology of X of the space X with G coefficients as of the homology of C lower star of X tensor G. We, instead of tensoring by G, we can also take hom into G. I will explain in a minute what this means. Okay, now I've written some formulae, and now let me just comment on these. So first of all, the names. The homology of the complex on the right is the homology of X with coefficients in G. Well, the name for the second graded abelian group is similar. But with an added prefix co. In other words, the cohomology of X with the coefficients in G. Or people also sometimes say with values in G. Which doesn't really matter. It's just another terminology for the same thing. Now, notation. The complex on the complex on in the right hand side in the first formula is denoted C lower star of X comma G. And while we're at it, the second one is denoted C upper star of X comma G.
Should we also have an upper star C in hom?
Yes, I will explain this in a minute.
Okay.
Now let's well the first complex, namely C lower star of X comma G, is more or less clear. We just take the singular chain complex, tensor everything by G, and we tensor the differential by the identity of G. Does this make any sense?
No, it's clear.
Okay, so in other words, we have let me represent it as okay. So we start with C lower star of x. And we have sorry, we need to start with 0. And so on. C naught, C1, C2. Okay, now C lower star of x, comma G is 0, C naught, comma tensor G, C1, tensor G, and so on. And well, the differentials get tensor 2, so here we have well, here we have nothing, but the first one well, the first one would be D1, and so the second one will be D2, tensor the identity of G, and so on. And this is clear. What about the second one? Well, the second one will be slightly different in that all the differentials will change direction. Which means well, the differential used to decrease degrees, and now it's doing the opposite thing. It's increasing the degrees of the elements. So here we will have Hom D naught G, and here we will have Hom D1 G. Sorry, it's not working. D1 G, and so on. Does this make sense? And sorry, here I forgot to put a G. Let me do this. Okay, does this make sense?
What is the Hom between the differential and the group?
Well, this means the functor Hom to G applied to the map delta naught. значит, функторы действуют не только на объектах, они еще действуют на отображениях.
Все.
Значит, мы берем функтор hom в g, применяем к отображению дельта 0. Мы что получаем? Тоже отображение. И так далее. So functors act not only on objects, they also act on morphisms, and here in the bottom line we apply the functor hom to g to delta 1, delta 2, delta naught, and so on. So the one thing we need to observe is this is this is not exactly a chain complex; it's a co-chain complex.
And I'm confused about the notation for the cochain complex here. That it shouldn't it be home of differential 1 in the first place? I don't see where theta 0 comes.
Yes. You're right. You're probably right. So you're saying this one should be delta 1, and this one should be delta 2. Yes, I agree. Sorry. Are there any more questions, remarks, and so on? And for co-chain complexes, instead of homology, we have cohomology. And we denote the result by H upper star instead of lower star. So this is the reason I put an upper star here, and also on the left. The only difference is the differential increases degrees instead of decreasing them. What else? Well, well, first of all, the resulting graded abelian groups have properties which are similar to the properties of the of the classical integral homology homology groups, and for homology with G coefficients, the result is well, the properties are very similar to the properties are similar to the properties of of the classical homology, except for the 1-point space we have we have the following answer. The homology of a point and with G coefficients in degree 0 is G. The remaining properties are exactly the same. For cohomology, things are slightly different. Slightly different in that the functor we get is contravariant and not covariant. Does this make any sense?
Yeah.
Yes.
Okay. Well, the properties are very similar to, they're not the same. I will erase the word the same. They're not the same, but they're very similar to but since all arrows are reversed, the we need to make a few modifications. Well, before I talk about this, let me also Let me also mention that we can define relative homology and also cohomology. Of a space mod subspace. And the recipe is the same as for absolute homology and cohomology groups. Namely, we take the chain complexes which calculate the relative homology and cohomology, no, the relative homology groups, and hypertensor those by G or take hom into G. Should I write this down, or is it clear without further explanations?
I think it's clear.
Okay. Wait.
It's okay. We can continue.
Okay. So well, given this, let me just state the basic axioms for homology, cohomology. Well, firstly, we have long exact sequences, but one needs to be careful because all arrows are reversed. So no, this one should be H of A. Sorry, my tablet is misbehaving. The long exact sequence looks exactly the way it does for homology, except for errors going the opposite direction, and the sequence should be functorial in x comma a. Now the second property is the second property is excision, which is exactly the same as for homology. Namely, suppose we have B inside A inside X, and the closure of B is contained in the interior of A. Then the map from A X comma A G to X minus B A minus B G is an isomorphism. Well, there's the homotopy invariance property. Homotopy equivalent maps induce the same cohomology maps and well, the fourth property is the cohomology of a disjoint union is isomorphic to the direct product of the cohomology of the factors. By the way, Tagia, what's the difference between direct sum and direct product, if any?
Indirect sum. So for finite, they're the same, but for infinite, in direct sum, we can have like only finite non-zero elements, and in product.
Yes. In a direct sum, only finitely many components may be non-zero, while in a direct product, anything is possible. Well, the last basic property is that we have the homology of a point which is equal to g in degree 0 and 0 in all other degrees, and if we remove this property and consider the remaining properties as axioms, we get something which is called a generalized cohomology theory. And well, generalized cohomology theories are usually defined for nice spaces, meaning polyhedra or CW complexes or some other category of spaces which are sufficiently well behaved. Okay, are there any questions? Well, what if I close this thing? Okay, let me save everything first. Okay, and then I'll try to remove the panel. Ooh, magic! The panel's gone, which is a good thing. Well, if, it's a good thing before I need to change the preferences. But let's worry about this later. Anyhow, are there any questions? Okay, now the most important property of cohomology is no, hold on, it's not working. Okay, there's still nothing. Okay. Okay. Now what do I do? Does anyone know how to toggle the panel on and off?
No, I don't know. I don't use Zoom at all.
Okay, so Wei, any suggestions, ideas?
I have no idea how to. Or maybe I saw there is a button on the right down corner that to plus new page. Shall we try to get a new one?
Well, yes, I can make a new page, but it's well, it's the same as the old one.
Oh.
probably not too difficult, but okay.
Can you see I'm drawing something?
Yes, you're drawing something, and the problem is I don't have I can't change. I can't turn on. I can't turn on the pencil. Instead, it's not it. This is not it.
I turned on my pencil at the bottom. That is to turn off the sound somewhere above there.
Somewhere
Into above the microphone.
Oh yes,
option.
yes. I see. Yes, I think I got it. Okay, so yeah, it's working. Let me erase this. Okay, so the most important property of cohomology is not on the previous page. But the most important property is that the cohomology with ring coefficients is again a ring, and we'll talk about this in much more detail later on. And it so happens that the dual statement for homology is not true. So the homology with ring coefficients is in general not a co-ring. Except when R is a field, then we get a co-algebra. But in general we don't. Okay, now we will define the ring structure and also see why this structure gives one new information which wasn't there to in which the just the additive structure does not know, and so on. But first, let's think a little. Yes. I'm trying to think of an example where homology with coefficients is really useful, and well, there are plenty plenty of examples. Okay, well, let's do one of those. So the one example. There's the Borsak-Ulam theorem, which says that a map F from Sn to Sn a map F from Sn to Sn is even, respectively odd, if and only if, for every x in Sn, f of minus x is well, f of x in the even case and f of minus f of x in the odd case. And what do Borsak and Ulam tell us? They tell us that the degree of an odd map from Sn to Sn, and all maps are assumed continuous, and the statement is that the degree of an odd map is odd. Does the statement make sense? Tagir.
Yeah.
Wait.
Yeah, it makes sense.
And well, in particular, an odd map is not homotopic to a constant map. And there are well, this theorem is probably second only to Brouwer's fixed point theorem in the number of applications it has in various parts of mathematics, which have nothing to do with topology. And in particular, they say that the statement is somehow useful in computer science. Unfortunately, I don't know. I don't know what exactly happens there, but apparently, apparently people are able to people were able to find applications of this statement, and there was a whole book about Borsuk-Ulam's theorem, which you probably can find online, and and this book discusses many of those applications. Well, I don't remember the name of the book, but it's easy enough to find on Google. Okay, well, before we do this, let's briefly discuss the easier case. There's a similar statement for even maps. The degree of an even map from Sn to Sn is even. Are there any ideas how to prove this statement? Well, let's take an even map from Sn to Sn. Well, since the map is assumed even, it factorizes as the composition of the map from Sn to Rpn, and then some map from Rpn to Sn. What do we do? Well, what's the next step? Wait. How do we prove that the degree is even?
Maybe we can somehow prove that the degree of F is the product of these two, or of degree of these two maps. But
Sorry?
the first map. Maybe we can show that the degree of F is the product of degrees of these two maps, but we know that the degree of first one is 2.
Well, to begin with, the well, there are several ways to proceed, and let me and one could use integral homology, but instead one could use homology mod 2, and well, in homology mod 2, we sorry, my tablet is not doing what it's supposed to do. Okay, let me just turn this off. Okay, so we did define the degree of a map in in the integral, the degree of a map between compact orientable manifolds of the same dimension using integral homology groups. Namely, one can define the degree of a map of compact connected smooth manifolds. Without boundary. And this degree will be an element of Z by 2. And smooth connected manifolds without boundary as sorry. So we consider the map of the homology groups of the nth homology groups, where n is the dimension of the manifolds, which is assumed the same for the source manifold and the target manifold. And depending on whether the map of the top dimensional manifold is an isomorphism or not, the degree is defined to be 1 or 0. And this time, the manifolds are not assumed to be oriented or orientable. They can be well, they actually are orientable in the sense that well, in the same sense that we talked about a month ago or so, and the well, the difference between integral homology and homology mod 2 is that for homology mod 2, all manifolds are orientable. Does anyone remember the definition of the homological definition of orientability? Anyone? And well, I think we talked about this, but I'm not completely sure. What do you think?
I don't remember that we talked about this.
Nor do I.
Okay. So, well, let's say something about this. A connected manifold without boundary is Z-orientable if well, there exists for every x in M, there exists a let me call this manifold M, there exists a class mu x and let me also call the dimension n. There exists a class mu n mu x, sorry, inside Hn of m minus x z. By the way, no, we did define everything using homology, so let me replace cohomology by homology. Okay, let me change this this thing to make it more well for compact manifolds. There is an easier version. So let's assume that the manifold is compact, or a connected compact manifold M is Z-orientable if there is a fundamental class mu inside Hn of M such that then and then I will change this part then for every x in M for every x in M there is the restriction the image of mu in Hn of n minus x is a generator. An equivalent definition, and we will see why those are equivalent. Did we see the second definition?
I think yes.
Okay, so we did see the first one, but not the second. Okay, this is possible. So let's Now, if we replace z by z2, then all compact connected manifolds without boundary become Z2 orientable. And in particular, the map of the nth homology groups induced by a map of compact connected manifolds without boundary of dimension n is either an isomorphism or it's zero. So the degree is one when the map is an isomorphism, and zero if the map is zero, if the induced map is zero. Same as in the case of integral homology, the degree is the number of pre-images of a regular point of a regular value mod 2. And this can be proved in exactly the same way. We proved a similar statement for integral homology. Does anyone remember what we did for integral homology? There are two definitions of a degree. One is obtained using just homology groups, and the other one is obtained by taking a regular value and then counting the pre-images with science. Does anyone remember anything at all about this?
I remember only the definition where we have the pre-image of a regular value, and then we have +1 if it preserves orientation, -1 if it isn't. But
yes.
I didn't remember about the proof.
And we did prove that the degree in the Z case. In the Z case, we In the Z case, we have two definitions of a degree. Firstly, we have the induced map of the homology groups, and if we are given the orientations, we can identify both the source and the target with the Z, and then we get a map from Z to Z. It's multiplication by some integer, and this integer is the degree. This is one definition. And the other one is obtained by counting brain images with science. And we did prove that both definitions give the same result. Tagia, do you remember this?
I don't remember the proof.
Okay. Wei, do you remember this?
No, I need to look at my notes.
Okay. Well, let's. Well, in this case, I do remember that we did talk about this, but maybe we need to discuss this argument once again. In the mod 2 case, both definitions make sense, and a similar argument shows that they are in fact the same. Does the statement itself make sense? Meaning what I've just said.
Yes. Yeah.
Okay, so we'll talk about the two definitions later, but the degree of the map from Sn to Rpn is 0. Well, this is basically because in this case we have a non-ramified covering, and all elements of RPN are regular values, and they all have 2 preimages. And then the degree is multiplicative, which implies that the composite map will have degree 0. The degree mod 2. And well, the last thing we need to notice is that the integral degree mod 2 is the degree mod 2. Which basically is which can be proved using either definition, but it's more straightforward using the definition which involves the preimages of a regular value. Wait, does this argument make sense?
Yes.
Tagia, same question.
That's clear.
Okay. Well, let's save the notes. Okay, so next time we will prove Ulam's theorem, and in the meantime, Tagia and Wei, please look at your notes. If you can't find the argument which says that the two definitions of a degree are equivalent, please let me know. We'll talk about that again. But I'm pretty sure we did discuss this at some point or another. And maybe even for arbitrary, we did say something about arbitrary homology theories, although I'm not sure. But for standard homology and cohomology, we did see this argument when we take the source manifold and collapse everything except some neighborhood of the pre-image of a regular value. So we end up with a map from a wedge of spheres to the sphere, and we only need to understand what it does to individual spheres. Гер, помните, значит, рассуждение было такое, что мы берем прообраз, значит, прообраз регулярного значения и схлопываем значит, в сорсе мы схлопываем дополнение к прообразу некоторой окрестности регулярного значения, а в таргете мы схлопываем все, кроме вот этой самой, значит, окрестности. У нас в таргете есть регулярное значение. Берем его окрестность, схлопываем дополнение в точку. Потом смотрим, что происходит в прообразе. Значит, там прообраз регулярной окрестности. Схлопываем, опять же, дополнение в точку. Получаем отображение из букета сфер в букет сфер.
Да, теперь вспоминаю.
Okay, so Tagia seems to remember. Wait, how about yourself?
Then I will check the notes. I will give you feedback on Monday when we meet.
Okay. Yeah, so it's an important theorem, and if people aren't still sure about what's going on and how to prove this theorem, no problem. We'll talk about it again. Okay, so the next meeting will be on Monday, usual time, usual room.
On this Monday, yes.
Yes, on the coming Monday.
Okay.
Next week.
Mm-hmm.
Okay. Are there any questions? Questions, remarks, comments, and so on. Criticism, maybe. No. Okay. Let me save the notes again. I don't want them to get lost. Okay, I will put the notes in the course folder, and I will I can put the recording there as well, but I'm running out of space on Google, so I don't want to put it there permanently. So if there are people who know how to post things on YouTube, please let me know, and then I'll put the recording on in the folder, and plays it once it's online on YouTube. Okay, well, then this is it. I think we're all a bit tired. Let's call it a day, and see you all on Monday.
Thank you. See ya.
Okay, see
You're
you.
welcome.
Yeah, I recall that there is one thing that probably can be off recording because it's not related to this course.
Okay. I'll